Good morning, everyone. Okay, today we're actually going to depart a little bit from what's on the syllabus. After going through a lot of the project proposals, I realized there's a bit of interest in doing some unsupervised learning, so I'm going to try and cover some of that today. Also, on the syllabus, actually, I had left Tuesday as no lecture, and that's because I was actually supposed to be in Mexico, but then because of coronavirus, I will not be. So it's kind of up to you guys. We can decide whether or not to keep the lecture off, or I can add more content. We'd probably be talking about introducing reinforced learning and maybe some neural network stuff. So maybe you guys can let me know in chat. Let me see. I guess not everyone is here yet. Maybe I'll ask again at the end of class. But think about if you would rather have a little bit more time to work on your projects, or if you want more lecture material. Okay, so let's go ahead and start off because there's a little bit more material today, I think. Before we talk about unsupervised learning, I wanted to polish off our discussion about non-parametric approaches. So we have kind of slowly been building up to get to sort of more non-parametric stuff from our basic linear equation, right? So we go from that to polynomials and also stepwise, and then we're starting to do a combination of those to do splines, and sort of we looked at a couple variety of common splines that people use, right, from cubic splines to natural splines, and then today we'll start off in a super different direction where we can look at similar ways of getting predictions that are done in sort of like a totally different procedure. So this is going to be kind of analogous to when we were talking about logistic regression, and then going to the k nearest neighbors, which is doing some sorts of nonlinear predictions in a fairly different way than sort of approaching this with a traditional equation that we're assuming some kind of modified functional form. And so what we're talking about is known as a kernel regression. And so what I'm going to do is I'm just going to write out the equation, and then we can dive in a little bit more conceptually to see how it works. So Q of x is equal to sum of k xi x over h So this equation is going to be more kind of just for your reference. I'm not even going to spend so much time talking about exactly what's going on in this equation here. I think one of the key things to note is this parameter h, which is known as bandwidth. And I'll talk a little bit more about this um, after we go through the concept of the kernel regression. Okay, so here's the concept. Suppose we've got a couple points like so. And let's go ahead and put in this red point here. And so the question that the kernel regression is essentially trying to answer here is, at this x, what is y? And so it's mainly gonna be a way of doing prediction. Again, there isn't going to be any way to do kind of inference here. And so in this manner, we're going to think of this as similar approach to our k and n, k nearest neighbors. So kernel is based on weights. If we weight points more heavily, when they are close, let me see a better way of doing this. Okay, so if close, then what we'll see is that these guys will play a sort of bigger role in influencing the position of my x, right? So maybe maybe this particular x is halfway between these two, and then these guys, you have not much of an effect. Okay. And let's see. On the other hand, if we decide if weighting includes far points, then all of these guys may end up having an effect, right? And so if I average all 5 of these guys, then maybe my x goes up to something like that. Okay, so it's a fairly simple way of basically saying, oh, I'm gonna kind of look at the nearest points, depending on a parameter, the bandwidth, which lets me say, look within a certain amount of distance. So h is the bandwidth. The larger it is, the more we consider farther points. the smaller it is, the more we consider local points. So in that equation where I had this this guy over here, H normalizes xi minus x when big, and H magnifies xi minus x when small. Okay, and so you can kind of imagine sort of what's going on here, right? And you may have a question about, okay, what is this sort of k function? And that is actually a flexible function that's that that describes your kernel function. Okay, and so what do I mean? So there are a couple examples of k of x. You've got what's known as a box kernel. So k of x is equal to, so this is a pretty common one, 1/2 if x is less than or equal to 1, and then 0 otherwise. You've got a Gaussian kernel, which as you can imagine looks like kind of like a normal distribution. So this is 1/2 pi exp negative x squared over 2. And then there is the I'm not even going to say how to pronounce it because I have no idea how to pronounce it. This one's a little bit more. It's kind of similar to the box kernel actually. And I think the main point here is that I wanted to introduce folks to the different types of common kernels that are used. It can be a little bit less straightforward to understand, exactly how these different types of kernels will affect a particular outcome. I think you kind of try a couple of them and see see what they do to your results. They can be kind of particular to the problem that you're working on. But really, in practice, choice of H is most important. And how do you choose the H? Same thing we've always been sort of saying, right? H is the parameter that controls how tightly you fit to the data, and so as your H gets really large, you're more subject to bias. As your H gets really small, you increase the variance of your results, and therefore, to get a balanced H, you want to do cross-validation, out of sample validation with like a k-fold. Yeah, so same story as always. So in one moment I will demonstrate how to perform kernel regression, and then we can take a sort of closer look at exactly how it's fitting to data. But before that, I wanted to talk real quickly about splines versus kernel regression. So kind of at the end of the day, these guys are doing similar types of things where you want to essentially get the best non-parametric or semi-parametric fit to data as possible. And they're both doing prediction. And so when is it, why is one better than the other? When should you use splines versus kernels? So I'll talk a little bit about why people choose splines. So computational speed. Splines tend to be faster. If you think about what a kernel regression is doing, right? I'm comparing basically a prediction of a data point against all the other data points in my regression, and depending on your bandwidth, depending on how many points you're predicting, that can get computationally intensive. Some people think that splines are a little bit simpler to understand and interpret, especially sort of as a derivative content of building on this sort of logical extension of the linear regression, going a little more complex to polynomial, combining with stepwise, then making sure you have the not constraints. So some people will argue simpler, and then clarity of controlling curve directly, right? You are still able to maintain some kind of relationship with your x's and explanatory variables going into this sort of regression, whereas the kernel kind of does everything together automatically. So kernels are easier to program, easier to analyze mathematically, right? You don't have to deal with any crazy basis transformation functions that get plugged into this into your linear sort of regression equation. It's just that simple kernel equation. Easier to extend to multiple variables. And then combinations of discrete and continuous variables is easier. And I guess I actually didn't even talk about this. With splines, you can't really do, you can't easily do discrete variables in the context of splines, right? Because it's sort of by definition trying to fit a polynomial fit to describe the variable relationships, which doesn't really make sense with a discrete variable. Okay, so we'll keep that in mind, or you can keep that in mind as you think about if you do want to do these non-parametric approaches, which one may be better or worse to use for any particular approach. Okay. So let's go ahead and jump on over to our studio. Give me one moment. Okay, we are going to come back to our trusty nonlinear design here, where we are looking at these sort of set of points. I've quickly fit a linear regression, but this is exactly the same model that we were showing in the previous couple lectures to look at nonlinear fits. So clearly a very nonlinear model. And I'm going to load a library called NP, which I believe stands for, non-parametric. And so this is a library that contains a bunch of kernel methods, and we'll see how to apply those. So we need to order the x's. Okay, and so this is actually only relevant for doing the plotting. It doesn't, it's not going to affect the regression in any way. So I'm just preloading that ahead of time. So we are able to create a kernel model by using a function called npreg, and then we just simply do our regular sort of specification. I know that as we've jumped around with different functions, a lot of them have looked like this. Some of them are a little bit more particular, and you can look in the class notes that I post for the code to see how the inputs are changing. But in this case, it's just like the LM function. And then we have BWS, which stands for bandwidth. Bandwidth specification. And the bandwidth is the value for the H. And so here, let's just take a look at what happens as I select through a couple different bandwidths. So we'll start off with this one, bandwidth of 0.05, and then I'm just going to plot it. I'm going to plot the curve of the true function in red, and then I'm going to plot the fitted, which is my x's ordered, and then the fitted values from my kernel model 1, which is the regression. Actually, I'll go ahead and run the regression, and we can see what happens if I do a summary of it. And it basically tells you, okay, we use this bandwidth, and then it gives some residual standard error and an r² value. But notice that there is no selection for or there's no information about any of the explanatory variables, right? And that's because that's not how this regression works. It's like that, again, it's like the k nearest neighbors, where I'm just looking at how close certain points are. So it's not going to give me any of that sort of information. Here it's telling me my kernel type is a Gaussian kernel, which is one of the ones that I had described. You can actually change the kernel. Let me see, I don't remember the exact option, so let me get into the help. Let's see. should have some. It might actually be a higher level option, so it's not listed here. Oh, here we go. C kernel type, CKER type. This is where you can choose the option. So this one that I can't pronounce, and then the Gaussian, and then the box. Those are, again, super common kernel methods. And I would encourage you to, as you do this, you could try a couple different methods and see how it changes the results, especially with respect to your selection of the bandwidth and what it ends up doing. But typically they should end up with fairly similar results. Okay, so let's go ahead and run this and plot it and see what we get. Okay, so again, in the red, we have our true function, and in the blue, we have the kernel fit. I think it's pretty neat that, okay, so we can see that it's fairly close to the true function, right? And we were getting a similar type of thing with the splines. And so if you were to just look at the predicted outcome, they would look kind of similar, and you think, okay, well, these regressions are doing kind of similar things, right? But that's not at all the case, right? With a spline regression, it's this weird like transformation of your explanatory variables into these, cubic functions that sort of slice up all of your data and then join them in these knots that have these weird constraints to make them continuous as they connect. Whereas the kernel model is completely approaching this in a different way, where it's saying, okay, where are my closest points? I'm going to weight them and then figure out where to predict a particular point based off of how kind of close, quote unquote, this point is to the points that I'm training against. And so they're really, really different methods, but you can see are getting similar sort of results in being able to replicate our true function.
Alan, can I ask a question?
Yeah, go ahead.
So I noticed that for the kernel regression method, you didn't use any like predict function. Is it because, like you explained earlier, that just by the virtue of looking at the k nearest neighbor, it's already kind of doing that prediction in kernel regression?
So I ran the model, and then the predicted values are, instead of getting it from predict, it uses a function called fitted. So
Okay, I see.
yeah, so that's essentially what it's doing with the prediction.
Okay, makes sense. Thanks.
Yep. Okay, so let's take a look now at what happens if I decrease my bandwidth. So this is kernel model 2 is exactly the same as what I have above, but now I'm going to decrease my bandwidth. And so, right, as a refresher, when you make your bandwidth, your h, smaller, it's going to magnify points that are closer to my fitted value. And so it's going to put a lot more weight on the influence of close points compared to farther away points. So let's see what happens here. Okay, so you got to look a little bit closely, but you can see that there's a little bit more perturbations here compared to our 0.05 bandwidth. You can kind of see that happening in kind of the center. I mean, it happens kind of throughout, but it's more visibly available to see sort of at the edges and in this area here. And so the variance is sort of taking over. So we would look at this and say, okay, you probably have a little bit of overfitting going on, right? And we can see similarly, if I shrink it even more, we should be able to see a more extreme version of this happening, where it is starting to rapidly jump up and down, because that's essentially where the points are located. So now, by shrinking the bandwidth, it is putting even more weight on points that are close by, and you start to get this this line that is starting to jump almost from point to point, essentially. And now you're getting really sort of overfitting. Okay. And now let's go in the other direction. So we started with a bandwidth, the one that we think is a pretty good fit of 0.05, and we shrunk down to 0.01 to 0.001, and now we're going to go the other way. And so the bandwidth is getting larger, which will normalize, the difference between your predicted points and points that are a little bit farther away. So let's take a look at what happens to the prediction at larger bandwidths. So here you can see that that these points are starting to cause my fit to get normalized to the average values. And so essentially the way I would think of it is, if I'm selecting this point, if the bandwidth is smaller, it would fit closer to here with the red line, but as the bandwidth increases, it's starting to look farther out, and it's going to average against a larger number of points, which is going to bring this down. And I think we can see that effect a little bit more clearly. I'm going to just go ahead and bring in these guys here. So if I increase the bandwidth to 1 from 0.1, we can see this line here, which is, you can imagine that like a point over here is kind of the average of, a larger set of points. And so it's flattening the curve. And once you get large enough, if you guys are thinking closely here about what's been happening with the trend of this line, this is again kind of similar to my k-nearest neighbors. It's almost as though I'm looking across the full spectrum of points, right? And so by increasing the bandwidth window, I'm basically saying I'm weighting equally, points that are down here with points that are up here. So at a certain point, your bandwidth, if it's large enough, is just going to be the average, right, of all the values in your data. And so we can see that right here. And so you've got this horizontal line that sort of just goes through all of this data, and that line is representing the average value of your y's in the training set. So how do we choose the proper bandwidth? I've written another sort of cross-validation function. I actually, I should have looked into this before lecture. I can't recall if npreg has a built-in cross-validation. I'm kind of thinking about it now. It would seem silly that it doesn't. but let me take a look really quickly. It may not actually have a built-in way of selecting your bandwidth. And in that case, yeah. So in that case, you would have to do something like this. Okay, and so this is doing a k-fold validation, number folds. You guys have all seen this before. Hopefully you're all fairly familiar having seen this type of function a couple times. And so in my cross-validation, I'm going to essentially throw in a bunch of different bandwidth values and then figure out which one gives the best, which bandwidth gives the best fit. And so I run that, and you end up getting, I think, actually we can go ahead and take a look at that. So it's in the CB results. So I explicitly listed out what the best bandwidth is, and we can see 0.033. So I'll just go ahead and throw that in there like so. And if I go ahead and plot this, it'll look, I think, similar to our first plot, but it's going to end up being probably a little bit closer for out of sample. And you can see here the blue versus the red, fairly close. Okay. Okay, hang on. I see some questions. Oh yes. So is the bandwidth related at all to the scale of the x-axis? Yes, it is. And so, oops, hang on. Let's just see. In the equation where you are doing your kernels, you have this xi minus x over h, right? So your h is the bandwidth value, and that scales directly with whatever your x is. And so your bandwidth, that is exactly right. That a bandwidth of 5 would include all the points. And do note, right, that the scale of your x can be different depending on the context of the problem. So that's why we don't have like a standardized way of saying, hey, your bandwidth should be, between this value and this value. It really is dependent on what your x's look like in your own data, right? If you're working with really large scales, then your bandwidth can be really big, compared to a data set where your x's could be really small, and then your bandwidth would analogous be really small. Okay, and then another question. So what criteria is it using to compare? Yeah, in this cross-validation, the criteria is the mean squared error, right? Which is something that we can still pick out here. So we can get the mean squared error of the model with this $MSE, and it actually lets you do training and testing data. You can take a look at this function here, txstat, tydat, and then xstat and uydat, which is corresponding to training and testing data. So it does have some options for comparing sets of points in the model and in the built-in function.
Alan, to go off of that, and I think you've talked about this in a past class, but like, why wouldn't the overfit model be picked? Just like, is
Yeah.
that error is like, where is that error being captured?
Yeah. So if you have an overfit model, your in-sample mean squared error is always going to be smaller, right? Because you are subtracting the like actual point to your predicted, and the actual points are going to be located. Like you could basically draw a line through every point, and you'd have 0 mean squared error, in-sample mean squared error. The reason why you don't choose the overfit is because our cross-validation validates against out-of-sample data. And so in this function, I presented it with some training data and I'm presenting it with some testing data. And the mean squared error that I'm getting out of this function is this out-of-sample mean squared error. So if it's overfit, then the mean square error is going to start going up.
Yeah. Okay. Thank you. Makes sense.
Great. Okay, so this sort of concludes our discussion about these nonlinear approaches, and we sort of capped off the course with the sort of opposite end of the spectrum from a linear model, where we're assuming this functional form and maximizing interpretability. And then now we're at this thing where we're looking at splines and kernels, where we are not concerned with inference and are mainly trying to get predictions. And so, yeah, so this is kind of the conclusion of building that story. So we're gonna move in a different direction for the rest of the course. As I mentioned at the beginning, we're going to talk about unsupervised learning, which is a pretty different topic. But why don't we go ahead and take an early break here, so we can have a little mental break before we dive into the rest of lecture. So let's take 5 minutes and come back at 10:53.
Hey, Alan.
Hey, sorry, I was muted. Go ahead.
Yeah, no worries. I have a question what LDA stands for and if we've covered that in class yet.
Yes, we have. It's
Oh,
it's linear discriminant analysis. That was the lecture after the logistic regression where we were looking at uh, that car seat example with
right.
yeah. So there was the whole idea was you've got your
So,
logistic regression, the LDA, and then the KNN as different ways of looking at models where you have um, uh, discrete variable as your y as your response variable.
okay.
Yeah, if you don't remember, you can always look at the YouTube videos that I put up,
Right.
or my lecture notes.
Yeah, I remember the example, so that's helpful.
Yep.
Thanks.
Okay. Let's go ahead and dive into our next topic, which again, kind of to reiterate, this is a totally different thing that we're going to be talking about here. So unsupervised learning examines undetected patterns in data. So focuses on settings with only explanatory variables. No response variables. Okay, so this is a sort of model where we are looking at just X's and no Y's. Okay, so not at all analogous to anything that we've been doing so far. So in particular, this is not interested in prediction. It is more identifying subgroups among variables. And sort of implied in this is that you are unable to conduct validation. And for some reason, people kind of mix this up sometimes, right? There is no outcome on which you are training, and thereby, sort of by definition, you just have nothing to do any sort of validation on. So this is much more, well, okay, I don't know if it's a good way to put it, but it's more like art than science, right? Because you are coming up with some groupings based off of the data, but you're not really, at the end of the day, it's kind of your call as to, you know, what sorts of sets of groups that you decide to choose from the unsupervised learning. And so we'll see what a little bit more about what that means in a bit. Okay, there are two primary approaches. We've got one principal components analysis, which we've technically covered already. And so this is the reduction from your X's to your Z's. right, and we're not going to go so much more into this one. It's essentially the first step of the principal components regression that you can use for data visualization, or is pre-processing for supervised learning, which is essentially what we did in PCR, which is the principal components regression. And then the second approach is known as clustering, which I think is what some folks are interested in looking at for their projects. So we're going to focus on the latter one today. And so some of you may have already heard of this method, k-means clustering. So this is a simple approach to partition data into k distinct non-overlapping clusters. Importantly, one of the features of this kind of approach is that k must be pre-specified. Okay, so what I'm going to do is I'm going to write out the formal optimization algorithm for conducting a k-means clustering. Again, this is one of these more complex equations that are kind of for your reference, and then I'm going to talk through what the algorithm does qualitatively. So it's minimizing C1 through CK, and you are summing k equals 1 to big K of 1 divided by CK, sum I prime elements of CK, J equals 1 to P of xij minus xi prime of j squared. Okay, and this CK is the number of observations in kth cluster. Okay, what the heck does this mean? It's actually a pretty straightforward algorithm to talk about qualitatively. So don't worry too much about this math. I think once we talk about the algorithm, I think you can go back to this equation and see, I think, pretty clearly how it works. So there's two steps in this algorithm. Randomly, so this is our initialization step. Randomly assign values 1 through k to each observation. Okay, so let's suppose I have 1,000 data points and I want to group them into 3 groups. The first thing to do is I'm going to say, okay, for the first data point, I'm going to randomly assign it 1, 2, or 3. For the second data point, I'm going to assign it randomly 1, 2, or 3. And so now at the end of the day, you've got 1,000 data points, and they've been initialized into a random cluster, one of the random clusters that you're trying to look at. Step 2, iterate the following until no more changes. Okay, so 2a, for each k cluster, compute the centroid. So centroids are based off of the Euclidean distance. I'll just draw an example really quick just so that we can see what this is. So suppose you have a cluster of 3 points. The centroid is right here. It's the middle of all the points, that's all. So I've randomly assigned everything into a bunch of clusters, into a handful of clusters, and then I compute the centroid. And then B, assign each observation to cluster with closest centroid, Euclidean distance. And that's it. You reassign the points based off of how close they are to the cluster or to the centroid. And then we go back to A and we recompute the centroid. And then you reassign the points, and then you recompute the centroid of the new cluster, and you continue doing that until it stops changing. And then you've got your groups. Note scaling. Okay. Normalization is often required. So if you are working with X's, explanatory variables, although I really should stop calling them explanatory variables because it's just, they're not leading to any sort of response variable. But your X's are, if they are really different scales. So if you are doing something, what's something that just comes to my head, like an economic example where you are looking at clustering GDP versus unemployment. Your GDP is in billions, trillions of dollars. Your unemployment is in terms of like percent. So you want to normalize it. Otherwise, what's going to happen when I am measuring my Euclidean distances, or if I'm computing my centroid, it's just going to completely get swamped by the bigger thing. So you have to normalize your numbers if you want the X's to be weighted equally. Maybe you don't want the X's to be weighted equally, right? In which case you wouldn't do scaling or normalization, but typically you do. Okay, so let me attempt to draw an example of what it's doing. Actually, let me make this a little bit bigger. Okay, let's see. 1, 2, 2, 1, 1, 2, 2, 1. Okay, so let's say these are my data points, and these are just points that have been randomly assigned into we're going to have k equals 2, so 2 clusters, and the points have been randomly assigned. So 1, 2, 2, 1, 1, 2, 2, 1, and now I have to compute the centroid of my ones, which I'm going to eyeball here, and it's going to be like maybe right here is my 1. And then I'm going to eyeball my second centroid, which might be right here. Okay. And now, so the 1, 2, 2, 1, initially putting that into the graph, that's kind of step 1 of our algorithm. I've just done step 2a, which is to calculate the centroid of that group. And now I'm just going to reassign my groups. So I'm going to say, okay, what is this one closest to? It's closest to 1, so that's a 1. What's this one closest to? It's closest to a 1, so that's a 1. What's this one closest to? It's a 1, and so on and so forth. Same thing with this one. What is this point closest to? It's a 2. And it's going to look something like this. Okay, so that is step 2b. Now I'm going to go back to step 2a, and I'm going to say, what is the centroid? It's 1. For 1, it's it's this red 1 for the 1s, and it's this blue 2 for the 2s. And then you reassign the groups to the closest centroid. Hey, look, it's not going to change, right? Because all these 1s are going to stay the same, and all these 2s are going to stay the same. And there we have it. These are the groups for our k-means. So pretty straightforward algorithm. And one thing to note is that this is a nonlinear optimization. So if I jump on back to here, we've got this whole thing going on, which is nonlinear. And so you may actually get, so for the folks who are a little bit more familiar with optimizations, you may get local minimums, which means that you could have different answers depending on what points that you start with. So with a k-means approach, you typically want to run it a couple times with a couple different random assignments of your initial one. So in step 1, you want to be able to do step 1 a couple times to make sure that you're always getting the lowest objective function value, and it'll give you the best groupings possible. So it's usually good practice to do that. And again, okay, this is something I probably should have checked before lecture, but the built-in functions, I believe, can have the ability to do some iterations to do this, although it's something that I would have to check. So let's go ahead and jump into R and take a look at how we would do this in code.
Hey, Alan, just to clarify.
Yep.
The centroid is not an existing point in the data. It's
yep, exactly. It is a calculation based on the points in the cluster. Okay, here we go. Okay, sorry, I think I missed a question. So if you get different results based on different iterations. Would you choose the final answer based on the most frequent clustering result? No. No, you would choose the answer based on, okay, it's not going to be there anymore because I switched screens. But that equation, that minimization equation, will come up with a specific value, and you want the one that returns the smallest value. And let's see, I didn't look at this before, but that's definitely a value that you're going to be able to extract from running it. And so I'll show how we can do that in the code, or hopefully I can figure out how to do that really quickly. Okay. So we're going to use a data set from the ISLR package. I'm going to load a couple more things here. It's okay, so we're going to do a pretty sort of simple example just so we can see how this is done. Okay, I'm gonna load in the auto data set, which looks something like this. MPG, cylinders, displacement, horsepower. And what we're gonna do is cluster based off of MPG and horsepower. So let's take a look at what that looks like first. So I'm gonna just quickly make a plot of my miles per gallon versus my horsepower. And so what let's see, what I'm actually doing here, I'm actually just doing the grouping against two variables, but you can do this across many or as many variables as you want. It's sort of easier to visualize this way. And if we have time and folks are interested, I could just throw in a bunch more variables and we can see what that looks like. But here is my MPG against horsepower, and this is what we're going to be clustering against. Like I mentioned, if I go back here, MPG is in the range of 10 to 50, right? And my horsepower is in the couple hundreds. So if I were to just straight up do my k-means against this, horsepower is going to completely dominate. And so I want to scale my data first, which you can do pretty easily with a function called scale. And I'm just going to include the two variables of interest, MPG and horsepower. So that's my scale data. If you want to see what this looks like, it is essentially scaling all the data to the same essentially range. So now my MPG and horsepower don't really look like anything compared to their original form. They're all relative, gonna be the same. They're just scaled. So as I mentioned before, with k-means, you have to explicitly select the number of clusters, which I'm just doing 2 clusters in this, and then this is my data input auto.scaled. And actually I can see here that at end start, and I'm pretty sure this is gonna be the way that you do multiple iterations. Let's actually take a quick peek at that. yes, how many random sets should be chosen? Maximum iteration is something to do with optimization, where it's going to continue iterating, right? So in that algorithm with 2A, or the 2A and 2B, where you repeat that, this says how many times before you want it to stop. We'll leave it blank, and it'll choose on its own. And number of starts, it defaults just to 1, but we could do a couple iterations to avoid this local minimum issue that I was talking about. For now, we'll just leave it like this. K-means.to, and if I look at this object, it will tell me the cluster means. So this is the mean. So I have 2 clusters. This is the mean of the MPG values in cluster 1. This is the mean in cluster 2. Again, they're scaled, so it's not really going to mean anything. You can calculate it later. So total sum of squares. Is that the value that you want to minimize? Yeah, I'm okay. I need to double check this. But I believe total sum of squares is the value that you want to minimize to do the multiple iterations. If you do it many times, you're gonna want to pick the one with the smallest total SS. I guess in practice we don't need to worry about that, because you could just do n star equals like 10. It'll run like 10 sort of random starts, and it'll pick it automatically for you. So don't worry about that, but do make sure to actually include that option, even though I'm not going to do that in the example for now. So this clustering vector, this vector of 2s and 1s, are just the assign. This is in the same order as the data. It's just assigning that data point to cluster 2 or to cluster 1. And so I can go back to my original data in auto, and I can create a new column, which I'm going to call K clusters 2, and that's going to be equal to k-means.to $cluster, which is returning this vector here. And so what is this doing? If we go into auto, so here are all of our original data points, and I've created a new column, which is assigning the clusters that came out of my k-means model. And now I have this column telling me which cluster every point belongs to. And I can go ahead and plot that actually, so we can see what that looks like. Just copy and paste this over from my notes. So this is the same as before, but I'm just coloring them based off of the cluster. And it has divided the data in 2, where your clusters are selected via that algorithm. Yeah, this is kind of an arbitrary example. It's basically splitting the data in half. Sorry, I couldn't come up with a more interesting example, but we can take a look at what this looks like if I increase the number of clusters. And so I'm doing exactly the same thing, but I am changing the number of clusters, and we can plot this and see how the assignment of the clusters is going to change as you have more and more clusters. You can probably imagine what happens, right? It's just dividing the data into more groups. So this is with 3 clusters. You get something that looks like this. And maybe you could kind of do this visually, but this is like a mathematically robust operation that's happening. And the nice thing about this is you can go into as many sort of dimensions as you want. So not just having 2 x variables. In this case, the example is going to be simple enough that doing multiple random starts will, I think, pretty much always get the same answer. But that's not always going to be the case, depending on how complex your data looks. Okay. So that is k-means. And we are, so unless anyone has any other questions, we're going to do one more example of a different method of clustering for unsupervised learning. Okay, so I see a question, actually the relevant question that I forgot to mention, but good that someone caught on. How do you decide the appropriate number of k value for a data set? Yeah. So that is, so there are techniques that people use to decide, but at the end of the day, it's kind of arbitrary. There isn't necessarily a set exact sort of numerical way in which we make this decision. So this harkens back to what I was saying before about this being, you can't really validate it, and it's somewhat more art than science, where you are selecting basically what you think is the k that makes the most sense. That having been said, people do try to and have some quantitative basis for selecting the k. And let me see if I remember how to do this. Okay, if I look at a, let's see, if I look at this again, yeah, so, okay, I don't want to misspeak here, but I believe it's what people often do to select the cluster. Okay, and I'm going to make a note of this so that in case I get this wrong, I can correct myself next time. Give me one moment. Actually, I'll put it in the notes here. Yeah, okay, so I think what people do, yeah, it's this one. I'm sure of it. It's the ratio of the between, which is why they list it. It's the ratio of the between sum of squares divided by the total sum of squares. And you look at this number, and what people will do is they'll run a number of different clusters, and they're going to plot the change in this in the between SS divided by total SS. And what it's going to look like is it's going to be a non-linear plot that will roughly always look something like this. And they do this thing called the elbow method, where you choose the point at which there's like a kink in the data, or there's a kink in the value where you start to, oops, accidentally selected oval, where the change is smaller, it's smaller than some kind of cutoff value. I mean, it's a little bit arbitrary here, because essentially what you're saying is that the sum of squares that's getting captured for the centroid is below some kind of cutoff value, and then adding more clusters is essentially getting sort of less value. So what people do is they'll look visually for a kink in this ratio of the between SS divided by total SS as you add more and more clusters, and then they'll choose that elbow point as the number of clusters that you have, which is like kind of arbitrary, but I guess then you could, you can base it on something, which, I've done that. I have papers where I've chosen clusters based off of that kind of arbitrary value, but again, it doesn't really mean anything at the end of the day. And so this is one of the more qualitative difficulties of doing k-means, is that you have to come up with groupings based off of some kind of justification. People will do this type of thing I just described, but it's not really kind of a agreed upon metric. There's no reason why you couldn't choose more or less clusters in a sort of quantitative sense. And that is actually, well, the selection of the K is no way really around that. But I will say that the next technique that we're going to look at tries to avoid the initial pre-selection of the K in doing the modeling, which is a nice little benefit. So let's jump on back over. How much time do I have left? Okay, yeah, we should have time. Let's jump back to the whiteboard. And let's talk about a second clustering algorithm known as hierarchical clustering, also known as bottom up or agglomerative clustering. It's kind of a hard word to say. So this is an alternative method that does not require pre-selecting K, or the number of groups. And it's got this kind of neat set of results in a tree-based representation known as a dendrogram. Okay. Let's talk about what a dendrogram is, and we'll just go ahead and make a visual example. So maybe you guys have seen something like this before. We've got this little tree structure thing going on. So this is a dendrogram. These points here at the bottom are called leaves. The whole thing is the tree, and as you can imagine, these things are called branches. The farther up the tree branches fuse, the more different the leaf observations are. Okay, so it's pretty straightforward. Essentially, by creating a dendrogram, I am assigning all of my data points to this tree, and they are represented as final points on the leaf. And the nice thing about the tree is that, like I was saying before, you don't need to make any pre-selections of the groupings, because this represents the full possibility or full spectrum of groups that can be represented by the data. And so if the endpoints are the leaves, I can decide to make a cut here. And if I cut that right there, then you can divide my points into 2 clusters. Right? Because I've got this cluster and this cluster. I can go ahead and, oops. I can, so this would result, so cut here, and this would be 2 clusters. If I make a cut right here, this would result in 3 clusters, right? And so I have this cluster, I would have this cluster, and I would have this cluster. Okay. And likewise, let me just erase these real quick. If I were to make a cut over here, I would then have 5 clusters. Okay. One common mistake to watch out for is, suppose I have some data points A, B, C, D here. No conclusions can be made on the basis of horizontal distance. So we only care about vertical distances, and this vertical, there's actually like an axis here that's going to tell us how far apart the branches are fusing from each other, which tells us how different they are. But you can't say anything about horizontal distances. And so you may say that it looks like B is closer to C and D horizontally, and therefore B is more similar to C and D than A is. But what you have to remember is that there are a bunch of different permutations that I could have drawn the tree without changing anything. If I switch these 2 branches, then it would maybe look like A is closer to C, and that is not the case, okay? So horizontal distances in the tree doesn't mean anything, only vertical distances. So make sure to not confuse that when you look at dendrograms. Okay, so let's talk about the algorithm here, which is, again, I think fairly simple. So I think when you're first looking at this, okay, I think that the logic here kind of makes sense in terms of doing the cuts and assigning clusters, but how in the world are we making the tree? How do we assign values into leaves, and how do the branches get fused and formed? So let's talk about that algorithm. So one, each observation is assigned its own cluster. So n observations leads to n clusters. So two most similar observations are fused. So now you have n minus 1 clusters. Okay. And then this repeat until a single cluster is left. And then you have the whole tree. Okay. And now probably the question that you're asking is, what does most similar mean? So for individual points, this is similar to the k-means clustering. It's similarity on the basis of Euclidean distance. So basically how close they are with each other. Okay, and so that is logical, right? So if I have, points that look like this, if these two are the closest points, these are going to get fused in the tree. But then you may have a different question, which is, what the heck do you do for clusters? So once I've started moving up in this iteration, in this iteration, I'm going to have points that are being compared against clusters, or clusters getting compared against clusters. So what does it mean for two clusters to be similar? Similarity based on linkage. And there are 4 types of linkages. There is complete, single, average, and centroid. Complete, so the way complete works is largest dissimilarity. Okay, so I have a bunch of points in my cluster and I'm comparing it, let's say I'm just comparing it to one other point. It is going to do the distances of all of the points in the cluster compared to that one point. So it's going to do this pairwise comparison, and then it's going to select the largest dissimilarity. And so that's a cluster compared to a single point. If it's a cluster versus a cluster, it does all the pairwise combinations of point comparisons, and it picks the largest dissimilarity. For single, it picks the smallest dissimilarity, For average, it takes the average dissimilarity. And then for the centroid, it collapses the cluster into a single point, which is the centroid of that cluster, and then it compares that to the other point or the centroid of another cluster. So there's a couple different ways that you can do this here. In general, average and complete tend to have the most balanced clusters. And by balanced, I mean that as I sort of walk down the tree, the size of the clusters are balanced or they're similar to each other. Whereas in single, you tend to have, as you move down the tree, everything sort of goes into, or as you move up the tree, everything goes into like one cluster or fewer clusters that are pretty disparate in the number of points within each cluster. Okay, so that's the basic algorithm, and the similarity comparison is just based off of these linkages for the clusters. And in that way, you know, I can lay out all the points as leafs and then fuse them upwards via via the algorithm, and so you get a sort of complete diagram of all the possible groupings. So let's go ahead and take a look at that in R. Okay.
Alan, so
Yeah.
for the dissimilarities for the clusters, is that are those are still using or utilizing the Euclidean distance? But
yeah, exactly.
okay.
So it's going to look at the Euclidean distance for every point in the cluster compared to a point or to every other point in a cluster.
Okay.
Great. Okay, so let's take a look. Oh, we're going to just use the exact same example. So HC standing for hierarchical clustering, and the function in R is called hclust for hierarchical clustering. So we're going to do, you have to use a function called distance or dist, which is doing the distance metric, and then we're going to use the complete method here, and I'm going to go ahead and do the same thing for two other methods. Let's see, we're going to do the average and single, and we can run through each of these. We can look at what this looks. I'm not actually sure what it looks like. Yeah, okay, so it's giving some attributes of the dendrogram, but I think it'll be easier to just plot it to see what it looks like. It's a little bit messy because there's a lot of points, but hopefully we'll be able to see what's going on. So I'm just going to plot all of these in a single plot, HC complete, hierarchical clustering using complete, using average, using single linkages, throw them all together. And again, I think this might be a little messy, but we can see, okay, once it finishes, I'll resize the plots so that we can have a better sense of what's going on. Okay, I think it should re-render, right? Or not. Okay, oh, there we go. Cool, okay. So this is the dendrogram. And so this is what I was meaning by sort of more balanced. You can see here in the single linkage, right, the number of points included in a cluster is really different. But with complete and average linkage, they are sort of more balanced as I go down the tree. And if I make a cut over here versus if I make a cut over here, right, it's going to tell me what the sort of clusters are for any number of groups. So at the end of the day, you still have to make some kind of judgment call about how many groups that you want. But the nice thing about the hierarchical clustering is that you don't have to pre-select anything. It gives you all the group possibilities in a single sort of run. Okay, so let's go ahead and see what this looks like in terms of the assignment. And so I can get if I decide to cut the tree, you can figure out which leaves belong to a particular cluster. And so I'm just going to do that and reassign or create a column in my original data set similar to what I was doing with the k-means. And I'm going to call that HC cluster. I'm going to choose 2 clusters. And the way you do that is a function called cut tree. And you just put in the model and you say how many groups that you want. And that's going to return the points. And so we're going to do a similar thing as we did before, where we're going to look at the groupings for a different number of clusters by cutting the branches at different points. So here is with, oop, I didn't run these guys. So here is with 2 clusters. Here is 3 clusters, 4 clusters, and 5 clusters. So it's actually going to look kind of similar in this case to the k-means, but it's definitely not always the case that it would. And in fact, I actually didn't do this, but why don't we take a look at what this would look like if we did the single linkage, because I think that that actually will look kind of different. And let's take a look. So here's 2 clusters. Aha, and you can see that instead of splitting in half, I think the way when you do the single one, it's going to care a lot more about the outliers and grouping those guys together. So let's take a look at 3 clusters. Yep, outliers. 4 clusters. There's one guy over there. And 5 clusters. And so again, I just want to sort of reemphasize with unsupervised learning in general, this is more of an exploratory thing. So, you know, what is spitting out here in the grouping, this is not like wrong by any means. It's just a different way of deciding the criteria in which I'm grouping points together. And so again, this is more of your sort of personal decision and criteria about how to do the grouping, how to choose the number of groups, there isn't any way to do validation, so there isn't any sort of wrong set of groupings. It is just important that if you're doing this for anything formal, for like a paper or something, or for the class project, that you are really clear and explicit about what sort of method and assumptions they're using to do your grouping, so that we know, inherently what's driving those results. Okay, and so that kind of concludes our discussion about unsupervised learning today. These are kind of the basic methods of starting to do unsupervised learning. I will say, these are like k-means and hierarchical clustering are the two sort of really classic examples of unsupervised learning in machine learning. If you took a machine learning class and were learning about unsupervised learning, these are the two methods that they would teach you. And so, yeah, I think that this is that these approaches are sort of the again classical ways in which we are doing some of this exploration without having any response variable. So if you don't have a y and you're just trying to figure out patterns in the data, these two approaches are going to go a long way in helping you do these groupings. Okay, so that's it for today, but before everyone takes off, as I was mentioning at the beginning of class, I wanted to repeat because not everyone was here. Next lecture on the syllabus is actually a break so that folks can work on the projects if they want, but it was originally scheduled that way because I was going to be out of the country, but since I'm not traveling, obviously, right now, if you guys could let me know if you want to keep that break, which is totally fine with me, or if you want to add more, or have an additional lecture, that's also fine with me. So what do you guys want to do? You can, I guess you can speak up or type it in chat, or if you don't want to say anything right now, you can email me. But I should probably make an announcement to the class a little bit in advance.
I think you can make a poll on Zoom.
Oh yes, I can make a poll on Zoom. I'm being informed.
I think so.
Yes, add a question. Let's do this really quickly. Class or no class? Yes, class, no class. Save this. Launch poll. Hopefully this should work. We're neck and neck, 7-7. There are 19 people, so there's going to be a tiebreaker. Okay, it looks like the yays have it. So so yeah, I will prepare an extra class, and I guess we can make it optional. So I mean, there isn't going to be any material in the class that will be sort of on the homework, and so yeah, we'll just make it optional extra material. So if you really don't want to attend, it's not a big deal. So we'll say that there is class for next Tuesday. So I guess I will see all of you guys then.
Thanks, Alan.
Yep. Oh, I can share the results. There you go. Look.
Thank you.
Okay, so that's it for today. We will end lecture here. I'm going to stop the recording, and then, as always, I'll stick around a couple minutes if people have questions.